Hey guys, and welcome back. Today we are going to be learning about a new topic, and that topic is called equilibrium. Now, good news. I've been looking ahead at the this unit and the next unit, and if you're someone who does not like math, good news. There's hardly any math left. There is this topic, which is equilibrium, which involves no math at all for us, and then the next topic, which is going to be acids and bases, involves some math, but it's not too bad compared to the rest of the stuff that we've been doing. So, if you are a person who has been struggling with math, we don't have too much left. So, congratulations. That being said, let's take some notes. So, I would title your notes Equilibrium, like it is up on the screen, and let's move on. So, up until now, we've always talked about chemical reactions like this, where you have hydrogen plus oxygen, and then that gives you water, H2O. And it just goes in a straight line. But in actuality, many of them are actually like this. Now, if you look over here, you're going to see that this looks a little bit different than this. What do you think this means? Well, I got one arrow going to the left. I got one arrow going to the right. So what we're doing is we're saying, hey, this reaction actually goes both ways. You can combine hydrogen and oxygen to make water, but also you can disassemble water to make oxygen and hydrogen. And this has kind of been true all along, but I just haven't been bringing it up because I'm trying to just focus on the concepts that we need to know at the time, and let's not confuse each other by having this thrown into the mix as well in terms of learning stoichiometry and all that. But now that we've hopefully mastered that, let's talk about this new thing called equilibrium. So, for your notes, I would write down equilibrium is when the forward and reverse reactions occur at equal rates. So that means that the hydrogen and the oxygen are in equilibrium are making water at the same rate that water is decomposing or breaking down and making oxygen and hydrogen. So every time these two combine and form a water also breaks up and forms these two at equilibrium. To maintain equilibrium, a reaction will always try to do the opposite of what you're trying to do to it. So, for example, I got this equation over here. We got nitrogen plus hydrogen gives you ammonia. All right. Let's take a look at this on MS Paint, and I'm going to do some things to kind of show you what I mean with that. Quick warning ahead of time, there's going to be a lot of edits with this because in order to do things in MS Paint, I need to make it, and then there's part of this later you're going to see I'm going to wind up rotating, and in order to do that, I need to go into PowerPoint because Paint won't let you rotate a custom angle. So just so you know, the audio is going to be a bit choppy, like it's been edited, and that's because it has. So here we go. What you always want to do with equilibrium equation is write it out, and I would 100% suggest that you do this at home. Write it out, draw a line underneath it, and then make kind of like a teeter-totter, like a seesaw, like you would see on a playground. I'm talking about this sort of thing, like this, okay? When you have a seesaw, if one side is equal to the other side, it's going to be perfectly balanced. But if one side is heavier, it's going to go down and the lighter side is going to go up. And we're going to apply that same logic with this sort of thing. So in this scenario, you would write it all out like this. And then the question is going to say something like, which way would the reaction shift if we removed some N2. Okay? So let's think about this. Take a moment, think about it. Even pause the video if you need to. If I got rid of some N2, and we're talking about it's starting off in equilibrium, what's going to happen to my seesaw? If imagine there's two kids here and then they both equal this kind of fatter kid over here. What's going to happen if this one jumps off? If you remove some N2, what's going to happen to your seesaw? Pause it, take a moment, think about it. All right, so if the N2 jumped off, what's going to wind up happening is in the next step, the N2 side is going to get lighter because I didn't remove, if you're wondering what was the N2 still doing there, I only removed some of the N2. I didn't remove all of it. Otherwise, we wouldn't have an equation because where would the nitrogen come from in the ammonia? So this side's going to get lighter because some of the kid jumped off. So your equilibrium is going to look like this. Now with equilibrium, it doesn't like this. It wants to be in equilibrium where both sides are equal. And right now it's not equal. One side's heavier than the other. So it's going to shift in a certain direction. And here's what that's going to look like. What would I have to do in this sort of situation to get it back in the equilibrium? Well, imagine that there's like a big hand that exists. What way would the hand have to push? Would it have to push down on the seesaw in this direction, going towards the left? Or would it have to push down on the seesaw in this direction, going towards the right? Pause the video, take a second, think about it. So if you said that the big hand is going to have to push it to the left, that's going to be what winds up happening here. It's going to push down to restore it to equilibrium where it looks like this. So if it shifts towards the left, that's called which way of the reaction shift, it would shift towards the left. Then eventually in the next step, the whole thing is going to wind up looking like this in the next step. If I go and I push to the left, it's going to push this side down and it'll wind up being back in equilibrium. So which way is the reaction going to shift? It's going to shift to the left because our arrow, our push, would go to the left. And if I wanted to be really specific about it, which I will ask you to do as we get more advanced in this, I'm going to say that it shifts towards the reactants, all right, because the reactants are what's on the left-hand side. Reactants on the left, products on the right, okay? All right, so let's go back to taking some notes. When pressure increases, the reaction shifts to the side with fewer moles. So how many moles are on this side? We got 3 because 2 plus 1 is 3. There's 3 on the left-hand side of this arrow. How many moles are on this side? 2 plus 3 is 5. So it says when pressure increases, the reaction shifts to the side with fewer moles. So which side is it going to shift to? If this side has 3 and this side has 5, it's going to shift to the left because that had fewer moles, 3 versus 5. When pressure decreases, the reaction shifts to the side with more moles. So this side again has 3, this side has 5. If the pressure went down, it would shift towards the right because it shifts towards the side with more moles. So it's 5 moles here versus 3 moles there. It shifts to the right because there's more moles. All right. Now, I have provided to you on the Haiku page a video that I think would really help if you watched, because it's hard for me to show you what's going on, unfortunately, because of the technology that we have to work with. This video will help to show you what's going on in kind of full motion, okay? So you want to click on this video that is on Haiku, watch it, and then let's go back and let's try out some problems as well, okay? So go ahead and do that now. All right, so welcome back. We are going to be doing a few practice problems today. There's going to be the ones on this slide and then the ones on the next slide. And the reason why I'm doing that is once you understand how to do this, it's actually pretty simple. But I do understand that it can be hard to figure out how to go about answering it because it's kind of counterintuitive at first. So we're going to do a few more problems than usual this time, so that way you can feel more confident in doing it. So we have this sort of setup over here with these questions. What I would like you to do is to try it out on your own. I'm going to provide some music to you and see if you can come up with the right answers. Now, before I let you go and before I put that music in, first thing I want you to think about is, hey, you got this. I would highly, highly, highly suggest on your paper drawing out our little seesaw. Because in my experience, people who do this are way more likely to be successful in figuring out which way a reaction is going to shift by going about this right here. So we got our seesaw here, and when we go and add more O2 or remove some H2O or add some heat, you can see very clearly what's going to happen on the seesaw when that happens. So kind of work through the steps on your own. Now, I also wanted to say that each one of these is its own separate problem. So what's going to happen if you add more O2? Okay, what's going to happen in the seesaw? Which way is it going to shift? Is it going to be towards the reactants on the left or the products on the right? Then the whole thing resets. Then there's question B, all right, which is unrelated to question A. So if I remove some H2O, the seesaw was equal at equilibrium. If I remove some H2O, which way is it going to shift? And is that going to be towards reactants or products? So go ahead, try that out right now, and let's see if you get the right answers. And welcome back. So, question says, which way would the reaction shift if more O2 was added? So let's compare that against what you did, and let's see if you got the right answer. And if you didn't, let's think about where you went wrong, all right, and how to fix that sort of problem. So, if more O2 was added, that means that it's like another kid comes on and jumps on this side of the seesaw. So which way is the seesaw going to go? Is this side going to go down or up? If you said down, you're correct, because there's more weight on this side. So you're going to wind up with something that looks like this. All right, so you're going to have something that looks like that, where because we added more O2, this side goes down, and because it's heavier, because there's more O2. So the question is, though, which way would the reaction shift if we added more O2? Now, the most common mistake is people are going to say, hey, it shifts to the left because we added more that way. But remember, equilibrium is all about resisting change. So it's actually going to shift to the right, because that big invisible hand wants to restore it to this sort of equal state. So it's going to push, if you can imagine someone going and pushing on this side, it's going to push it down so that it looks back like this. So which way is it going to shift? It's going to shift to the right towards the product. So if you wrote down for this question, products as being the correct answer, you are right. Good job. All right, so the next question saying, hey, what's going to happen if some H2O was removed? So let's go back to our board and take a look. All right, so we have our setup here, and it's saying we're going to remove some H2O. So that's like there's this kid here. He jumps off the teeter-totter. What's going to happen? By the way, when I say teeter-totter, that to me, that's the same thing as seesaw. When he jumps off the seesaw, what's going to happen? Well, if you said that this side is going to go up in the air, you're right. So you're going to wind up with a situation that looks like this. So again, the right-hand side, the product side, is up in the air because we removed some H2O. Notice that this is the exact same look as it was in the previous problem when it said, hey, what's going to happen if we add some H2? So you can definitely get the same result with different items. If you add some H2 over here, it's going to go down. If you remove some H2O, this side is going to go up, and you're going to wind up with the same looking thing. So the question still remains, though, which way is the reaction going to shift if we remove some H2O? Which way would that big invisible hand need to point in order to get it to go back to normal, like this? Is it going to have to shift this side down, like that, and shift to the right? Or is it going to have to shift to the left? If you said that it needed to shift to the right, you are correct, because it's needing to push this side down so that way you get a nice equal playing field like this. So the correct answer here, if it's going to shift to the right, what's on the right-hand side? Is that reactants or products? The correct answer is it's going to shift towards the products. All right, so you're going to make more products. All right, so let's look at the next question. Next question says, what's going to happen if some heat was added? Let's go back to our board. All right, so which way would the reaction shift if some heat was added? Well, that means that more heat is going on over here. So another kid's getting on this side of the seesaw. What's going to happen? Well, let's take a look. All right, so when another kid gets on the right-hand side of the seesaw, it's going to go down because there's more weight on this side. So which way is the reaction going to shift? Remember, it's going to want to counteract that force that's bringing it down. So it's going to be shifting towards the left. All right? The big invisible hand's going to push down on this side to get it to go back to how it was. So what's on the left-hand side? Is that reactants or products? If you said reactants, you're right. Okay, let's take a look at the next set of questions. Let's see how you do. Just like last time, I'm going to provide you with some time and some music so you can try these out. I know that this lecture is a little bit longer, but like I said, I want to make sure you understand this because it can be kind of confusing and counterintuitive. So go ahead, try this out, make your seesaws, and let's see how we do. right, so welcome back. I left the recording running that time so that way you can see all the work that goes into setting this problem up. It would be so easy if we had in-class learning and I could just draw it on the board, but man, oh man, is there a lot of finagling to go around to get things to work properly. So, here's your equation. The question is, if some H2 is removed from the reaction, would the reaction have to shift to the left or to the right? Okay? So, if we remove some H2, what's going to happen? Is this side going to go up or down? Well, removing some H2 is like the kid jumps off the seesaw, so this side's going to get lighter, so it's going to go up. And you're going to have something that looks like this. All right, so when some H2 is removed, you're going to wind up with something that looks like this. It's going to be going up on this side. Now, which way is the invisible hand going to have to push it to get it back to equilibrium? Well, if you said it's going to have to push towards the right, you're correct. Now, what's on the right? If the question said, like, hey, is that reactants or products, what would that be? Products is the right answer. Okay. All right, next question. If the reaction was an exothermic reaction and some heat was removed, which way would the reaction shift? Now, one thing I want to point out to you is I didn't show heat anywhere on here. There's kind of an extra step. It says, hey, it's an exothermic reaction. So I'm kind of hoping that you remember what exothermic means and then put that into the equation yourself. So let's go back to our drawing board. So by saying that it's an exothermic reaction, I'm kind of saying that there's also heat being created on the product side because the side matters. If it's endothermic, there's going to be heat at the start because you need heat to get the reaction to go forward because it absorbs heat. That's what endothermic means. If it's exothermic, it means that you're going to be producing heat because heat's going out. It's a product, all right? Remember, like exo, X means out, like your X, it's out of your life, all right? So that means that I'm kind of extending my seesaw over here. And it's still remaining equal just like it was, because that was always there. It just wasn't shown before. So now that you have this sort of setup, maybe the problem that we had before becomes a little bit more clear. So let's think about what the wording on that problem was. So the wording says, if the reaction was an exothermic reaction, okay, we took care of that. We added that in. And some heat was removed, which way would the reaction shift? Well, hopefully, now that's becoming a little bit easier now that we've added this in, which is a step that you'll have to do. If I remove some heat, which way is the seesaw going to go? Well, if I remove heat, that means that this is jumping off. So this side is going to become lighter, and you're going to have this side going up in the air. So let's show that. All right, so like I said, we removed some heat, so this side went up in the air because it's less heavy now because heat jumped off and this side got lighter. Which way is the reaction going to have to shift to get back to equilibrium? It's going to have to shift to the right. So that means that if I remove some heat, more products are going to be produced. So the correct answer here is it's going to be shift to the right, more products produced. One final problem I want to ask you. All right, so here's the final problem. Which way would the reaction shift towards the reactants or the products if the pressure was increased or the pressure was decreased? So take a minute, try these out on your own. I'll put in some more music, and let's see if you get the right answer. If you need to refer back to your notes, I would 100% say do that. These are actually fairly easy once you understand the rule. So go ahead, try it out, and we'll be back in a second. right, welcome back. So, question is, if I increase the pressure, which way is this reaction going to go? Now, the good news is for pressure problems, you don't really have to do any of this stuff. You don't have to do seesaw stuff at all. You just have to follow the rule. Here's the rule, going back to our notes. Here it is. If the pressure increases, then the reaction shifts to the side with fewer moles. So in this example, there was 3 here, 5 here, so it's going to shift to the left. So when the pressure increases, it's going to shift to the side with fewer moles. Well, let's count the moles. 2 plus 1 is going to give me 3 moles on the left. And then over here, I only have 2 moles. This heat, don't worry about that. There's no moles here. This doesn't count for anything. It's just heat. It's not a chemical that's out there. It's just kind of like energy. So I got 2 moles here, 3 moles here. So which way is it going to shift? It's going to shift to the side with less moles, so it's going to shift to the right, to the product side. So if you wrote over here, products, you got it right. Okay? Now, what would happen if the pressure was decreased? Well, again, let's go back and look at our notes. No need for the seesaw at all. If the pressure is decreased, then it's going to shift to the side with more moles. All right? 3 versus 5, it's going to shift to the right. So let's see what side has more moles, and it's going to shift to that side over here. Well, I have 2 plus 1 is 3 moles here, 2 moles over here, so it's going to shift to the left, towards the reactants, because that side had more moles. It had 3 moles. The other side only had 2. Okay? If something will happen sometimes is, let's say that I had a different equation and there was 3 moles on the left and 3 moles on the right, and the question says something about pressure, and it's going to be like, hey, which way is it shift? Well, if it's equal number of moles on both sides, then there's no change. There's no shift because it was equal. Okay? All right, so your homework for today is going to be this sheet right here. All right? Now, what I want to point out to you is that it's 2 pages long, so make sure you do all of it. It's going to be the same format. You're going to take a photo and send it to me through Haiku, please. And I also want to point out to you that they're not really using chemical equations for most of these, except for the 2 at the end. So it's going to hopefully be a little bit more simple. Do realize that when they do this, 20 kJ, well, that's kilojoules. What's kilojoules a unit of? Well, it's a unit of energy or heat energy. So whenever it talks about this, it's talking about heat or temperature. So when it says over here for this question, it says, hey, the temperature's raised. You make your seesaw, I add more kilojoules of energy. So it's like another kid jumps on this side of the seesaw. Which way is the seesaw going to go? It's going to go down. So which way is it going to shift? Towards the left, towards the reactants. So the answer to this guy is going to be reactants, letter B. Okay? So go ahead, try these out. Remember to use your knowledge from before when it comes to these sort of things. If it is a delta H that's positive, referring back to reaction rates that we talked about last week, you're going to have endothermic, so heat's going to be on this side. If delta H is negative, you have heat going out, so heat's going to be on the right. So you might need to write that in so that you can do these problems. All right? Good luck. And let me know if you have any problems. Please email me.